heard yesterday the papers by Dr. Cohen, so now we're going to move on to paper 173 by President Stillman and Dr. Cosgrove. This is going to be presented by Dr. Cosgrove, and this is NMR self-diffusion studies of benzene and methanol in ZSM-5, not ZSM-5.
I think it should be ZSM-5, I don't know. Presumably because it was discovered in America, we have to use the Z form. So we only have Z form in England. My talk is going to be rather more qualitative than the last talk. We've used pulse field gradient NMR techniques to look at self-diffusion in zeolites. And this is a new venture for us. We've used these methods to look at polymer solutions and at the solid gas interface where the solid substrate is impermeable. So this is our first venture into this, and these are very new results. The advantage of using a complicated and expensive technique like NMR to measure diffusion coefficient is that we're using a molecular probe. All we're measuring in this experiment essentially is molecular displacements. And so we don't have to use the complicated non-equilibrium thermodynamics and all the other jargon that you need to analyze absorption resonance with NMR. Because essentially we measure a simple parameter. We measure how far molecules move in a given period of time. In fact, we don't need a diffusion equation to analyze the results. So my talk is in three parts. First, I'll say a little bit about how the NMR diffusion experiment works. Then I'll say a little bit about the description of the particular zeolite system we've looked at, and then talk about the NMR results at the end. So if I have my first slide, please. I don't really need to introduce the zeolite we're looking at. It's the one in the middle, ZSM-5. And it's an interesting zeolite because of the interconnecting channel structure. Essentially, you have these channels that are lying vertically on the screen, connected by a herringbone system of channels going horizontally. Now, in principle, then, NMR, we can do a lot with these zeolites if we could get a big enough zeolite sample. For example, if we could have, say, a millimeter zeolite sample, then in fact we could measure the diffusion tensor in this material. We could measure the diffusion in this plane and in this plane. But of course that's probably impossible to get zeolites quite that big, at least this form. Anyhow, first I'll tell you a bit about NMR. That's the wrong gadget. I need this one too. Right?
Yes, just stick that.
Oh, okay. It's got a heart. Now, a bit about NMR. The basis of NMR is the NMR relaxation times. And although in this particular experiment we don't need to measure the relaxation times or estimate what they mean, the systems are subject to the constraints of the relaxation times because these determine the timescales over which we can make NMR diffusion measurements. So relaxation is at the bottom of this, even though we don't use it too much. This slide isn't very easy to read, I'm afraid. This is just breaking down the NMR interactions. There are many, many contributions to the NMR line length. And these are just some of them. The Zeeman interaction, this splits the energy levels. The dipolar interaction, this is what wrecks most of the experiments on diffusion. Chemical shift and spin-spin, these are a complication, but they can be an advantage in complex systems. Because in principle, if you had two different diffusing species in all these materials, one could differentiate between them with chemical shift if the resolution was that good enough. Let's focus on this Zeeman term. This is a fairly noddy explanation of NMR. The magnetic field splits the degenerate energy levels, and the splitting depends on the magnitude of the applied magnetic field. And so if you make the magnetic field bigger and bigger and bigger, which in terms of NMR manufacturers means spending more and more money, you get more and more resolution and more sensitivity. In a conventional NMR experiment, we have a linear magnetic field. In other words, over the volume of the sample, the magnetic field is constant. And that's what one strives for in high-resolution NMR. In this diffusion experiment, we do the reverse. We've got a linear field gradient across the sample. This means that spins in different physical parts of the sample will have different effective chemical shifts. So from the shape of the NMR spectrum of these materials, we can say where things are in space. And this is the basis of the NMR imaging technique. Effectively what we do in the diffusion experiment, I have to explain this very quickly because it really is quite a complicated technique, is we take a snapshot of where all the spins are in space by polarizing the system and memorizing the position of the spin vectors in this magnetic field. So this is a magnetic mapping of where things are in space. Then we wait a certain time, we take another snapshot, and we correlate these two photographs. And from each individual position, we can work out how each individual spin has moved, and then this is obviously integrated over all the displacements. This is a picture of the field gradient, north-south magnetic fields, and the gradient varies continuously across the sample volume. So in the centre, we have the absolute resonant frequency. To the left, the field is slightly higher, and to the right, the field is slightly lower. So if we just had one spin in space, if it was on the left-hand side, then we'd know where it was from its chemical shift. If it was in the middle, it would be exactly on resonance. If it was to the right, it would be shifted in another direction. And so you can map these spin positions with a bit of simple geometry. This is what the NMR experiment actually looks like, and I'm afraid it's too complicated to explain in much detail. But you polarize the spin system at the beginning, and this oscillation here is the so-called free induction decay, the nuclear signal. We apply a pulse of field gradient. So at the point here, on the left-hand side, we instantaneously take our snapshot. We store where the spin positions are. Of course, this wrecks the signal, so you actually no signal after this, because effectively we dephase all the spins in the system through hundreds of radians. Then we wait. Now, the wait time is a unique feature of this experiment. We can actually define exactly over what timescale we're measuring diffusion. And typically, for the systems we've looked at for zeolites, the maximum diffusion time is 15 milliseconds. Now, with perhaps with a better system, we could expand that timescale. We can certainly go down probably to about 100 microseconds. But this gets quite hard because these magnetic field pulses are pulsed at 100 volts at 100 amps. And so it's quite an exciting experiment. It's like a gunshot going off when you do this experiment. So you kill the signal during this middle part. When you apply the second field gradient pulse on the right-hand side, the signal reappears again. And what happens is this echo signal we have at the end here contains the information on diffusion. And if we vary this distance between the pulses, or we vary their intensity, or we vary the size of the field gradient, then we can measure diffusion. This is another variation of the same experiment, and this is one that we've used in systems where the substrate has a high susceptibility. So in zeolites this isn't so important. For graphite materials like that, then it's important to use techniques like this. It's the same sort of idea, only instead of having one pulse, you have about 4,000 or 5,000 RF pulses, but it's all part of the fun of NMR. This is a picture of the NMR experiment, NMR apparatus. It's basically homemade. It looks like that, which proves it's homemade. Just to show you one overhead. Now this is about our zeolite system. This was ZSM-5, and this was created at ICI in England, and it roughly these parameters. It's a fairly high silica zeolite. It's got, well, no, it's not. It's probably a medium one, I suppose, on your scale. The silica to alumina ratio is 60. The BET area, total area, is 450 meters square per gram. It's got rather a high external area. It's rather a disappointment. I think this is a facet of the way we made it. The geometric area, because these particles are about a few microns, is only 2 or 3 meters square per gram. And this is a complication, unfortunately, in the data. The X-ray structure shows it is actually ZSM-5. It has a low iron content. This is something we set out to do because iron can really wreck NMR experiments, depending on where the iron is in the system. It shows a typical reaction profile if you undergo a typical sort of catalyst bed reaction. I just show some slides here. These are just typical of how these things react. You put methanol in, you get all sorts of gunk out the other end. Right. Now, the first thing we did was to measure some absorption isotherms. On these things, I'll show you very quickly. You can see this really should be a type 1 isotherm, but it's going up a bit, and I think this is just a feature of the fact that there is a high external area, and probably the surface of the crystals aren't very well formed, and we're getting some sort of capillary condensation or something in the surface. The green line is meant to show you roughly where we've done the NMR experiments I'm going to talk about. We've done a lot of these experiments, but let's give you a very quick view of what they look like. With benzene, it looks a lot worse. You can see it's almost a complete type 2 isotherm. So this is unfortunately because of the surface structure of the material. Now we did 3 NMR experiments on these materials. We looked at the normal low-resolution NMR spectrum, that's called FID. We've looked at the Carper-Cell experiment, and this is an experiment for knocking out chemical shift and heteronuclear dipolar interactions. So this could give us information, for example, whether our gas molecule is close to a heteroatom, for example, near an aluminium. And the DNCP, which is a very difficult experiment, this wipes out everything. If you put any material into an NMR machine and use this sequence, and you get a thin, narrow line. The advantage of DNCP is it takes out, as you can see from my bottom slide, heteronuclear and homonuclear and chemical shift effects. And the residual spectrum just contains mobility information, at least in these systems. And so by comparing these different line widths and line shapes, you can say something about the environment of the gas molecules and also their mobility. So we did this first just to have a look at the system to see if we could understand a relatively simple picture. I'm afraid this slide isn't very good because the chart recorder went bananas when I was drawing it out. This is the line width, and it's a fairly broad line. It's of the order of a kilohertz wide, and it can't be fitted to a single line. Now, most adsorbed molecules have a Lorentzian line shape, and this is to do one with the mobility and two with the dimensionality in which we find them. So fitting this to a single Lorentzian peak didn't work. Fitting it to a double Lorentzian peak worked quite well, and you can see the green line goes through the red line, or the red line goes through the green line, really quite well. That's a double fit. It's missing at the top, but that's a digitization error. So this gave us the idea that we're seeing two components in this system. One we think is inside the zeolite, and one is outside. And the mobilities tend to, the line widths tend to confirm that, because the width of these lines gives you some idea of mobility. So the narrow line, we believe, is outside, and the broad line is inside. The Carper-Cell experiment, this is a better experiment really, because you can collect a huge number of data points, and we know that the decay constants for this experiment are exponential. And again, we see the same sort of thing. We see a fast component and a slow component. The fast component corresponds to the immobile species. The slow component corresponds to a mobile species. And again, the double fit looks quite good. With the ultimate decoupling experiment with DNCP, if anyone wants any more details about this experiment, I'll tell them about it afterwards because there isn't time to do this at the moment. Again, we get a very good fit to a double exponential. So we do have two different environments. We have molecules moving fairly slowly and molecules moving relatively quickly. And we're seeing a superposition. Now, all these time constants are coverage dependent. This means that the situation is nowhere near as simple as the one we see here. So there's exchange between environments inside the material, and there's exchange with the surface and the gas going in one zeolite, coming out of the other. There's a whole lot of exchange processes which are behind these experiments. And we have managed to make a stab at what they're like. Now, first diffusion experiment. We've measured, this is methanol on the ZSM-5 at 3 different temperatures. And the first thing that happens is when you measure the height of the spin echo as a function of either the magnetic field gradient or the diffusion time. This is a 15 millisecond diffusion time. Now, if this was a single diffusing species, these would be perfect single exponentials. If there were no other constraints, in other words, if it was totally free diffusion, these would be single exponentials. It turns out they fit rather well to 2 exponentials. And of course, the data is a bit noisy. And I should say these experiments are almost on the limit of what you can do with NMR because of the relaxation times. So these seem to fit to 2 exponentials and fit rather well. So what we've done, we've taken the slow component as a function of temperature, and I just plotted it here. I bet this is an awful graph because I forgot the original data, so I had to make this up in the hotel room last night. we see this rather interesting effect. We plot log D. Now this is almost certainly mainly the intra-diffusion coefficient against 1 over temperature. You see a very complicated looking behaviour. At low temperatures, we see the diffusion coefficient is increasing with increasing temperature, and naive interpretation of this is this is mainly molecules inside the zeolite which haven't travelled far enough to reach some sort of boundary. And if you put the diffusion coefficient in and the size of the crystals, that seems to look roughly right. It turns over, and this is, I think, seeing some sort of restricted diffusion. We're now seeing the barriers of the constraints of the size of the crystal, and then if you give it a bit more energy, they can get out and we see diffusion into the gas phase. So this is a rather naive explanation of this, but it's just how we see the data at the moment. I should say that the group at Leipzig have done a lot of work on diffusion in zeolites and have seen similar behaviour in zeolite A and other materials. Lastly, I'd like to just show you a different way of interpreting this data, because the interpretation here is based on using the diffusion equation to get diffusion coefficients, and that probably is rather naive in a system where you've got so many different constraints. And an interesting experiment you can do, an interesting thing you can do with this data is say, well, let's just take the attenuation, which is basically related to the space correlation function, and Fourier transform it. And if we do that, we get a picture that looks like this. Now, there's no modelling this at all. This is just taking absolute spatial positions and correlating them. We can get what's called a propagator. This gives us the probability that a molecule has travelled a certain distance in the diffusion time of the experiment. And these are the three graphs Fourier transform. This is quite a trick as well. If anyone knows anything about Fourier transform, just try and Fourier transform this data. It's a headache. Anyhow, these are roughly right, I think. What we see here is that as we go up in temperature, the probability of getting a further distance increases as you'd expect. And obviously you can do all sorts of calculations with these probability profiles in terms of residence times, passage between zeolites, and so on and so forth. These are very new data, so we haven't really gone to town on what you can do with them, and we need to do a lot more experiments, I think, before we can come to any real conclusions about how useful this sort of data is in this work. So, I mean, qualitatively, we just see the temperature effect here. The interesting thing about the probability is, of course, this is not an impossible thing to calculate, and we've had a naive go at this as well. And I'll just show you this graph, although I don't think I've time to explain it very much. This is using a sort of Monte Carlo method to look at percolation through a zeolite. And you can see the probability of travelling a certain distance. If you start one molecule at an intersection and then just let it drift around randomly, and you can put constraints on the probability of another molecule in an adjacent cell. You can put adsorption in. It's quite a non-mathematical way to model these things. So the Fourier transform of these plots, in principle, ought to be able to give us something akin to the experimental data, although we've got a long way to go. You can see here that at short diffusion times the molecule is constrained to where it starts, and if you let the diffusion time increase, that's going along this way, number of steps travelled, and of course there's a probability that it will reach the second cage. If you make the window bigger, that's coming along this axis, then you can see there's quite a high probability that it goes up from the first cage into the second cage. Now, this is very short time behaviour. Clearly this has got to be, we've got to think of something. We've either got to get the NMR experiments down nearly an order of magnitude in time, or get a Cray computer to go any further with these. But at least this thing is, the reason we're showing this is to show that this propagator is something that's amenable to calculation. I'm sorry that's rather a quick talk on this, but that just gives you a view of what we're doing. Thank you. Yeah, we've done some of these experiments at lower coverages, and what happens is the two populations change. As you go to lower coverage, we finally get more of the broad component and less of the narrow component, and the diffusion coefficient increases. So we see more mobility and we unpack it. I've got some more data on that.
Say something about the jump distance per unit jump.
Not directly from these experiments. From conventional relaxation methods, you get a relaxation time, and from that if you do a correlation time, you get a jump distance. But we've avoided that really because if you don't have to put that into the model. All we know is that over 15 milliseconds, the molecules have moved a certain distance. You could step that back, I suppose.